A jackup rig operates as a highly stable, elevated drilling platform, pinned firmly to the seafloor. To reach a new location, this massive steel structure must now be lowered directly into the churning wave zone. This creates a strict operational paradox. The rig is engineered for stationary rigidity. Converting this top-heavy silhouette into a floating vessel introduces an inherent engineering compromise. Afloat, the Jackup possesses extremely low freeboard, meaning the deck sits perilously close to the waterline. The hull is also perforated with numerous hatches, vents, and doors leading to internal compartments. Once buoyant, the ocean exerts extreme dynamic forces on the hull. Heave, roll, and pitch are severely amplified by the leverage of the hundreds of feet of steel leg now extending high into the air. The physical hardware of the rig cannot entirely neutralize these forces. The structural design prioritizes drilling functionality over marine seaworthiness. Survival during transit relies entirely on human intervention. Marine specialists, towmasters, and rig movers enforce strict phased checklists to protect the vessel through the state change. The process operates on a framework known as pin-to-pin. The move is broken into 6 distinct phases, and the rig cannot progress to the next physical state until a specific procedural gate is cleared. Moving a jackup involves the active management of shifting physical states, where structural integrity depends entirely on exact procedural execution. Phase 1 begins before the hull ever touches the water. Crews work through exhaustive pre-move checklists to calculate afloat stability limits and secure all loose equipment. Mundane items like the blue and red skips, half-heights, and drill pipes become lethal threats once the rig is moving. If a container breaks its lashings in a swell, it will batter main ventilator trunks and destroy the rig's watertight integrity. This cross-section diagram shows the first major system handoff. While elevated, the rig pulls cooling water through deep well pumps on a lowered tower. As the hull enters the water, the crew must manually switch the intake over to the hull's internal sea chests. This transition occurs at exactly half-floating draft. Poor planning or a delayed valve sequence here leaves the rig stranded, neither fully pinned nor fully buoyant, with its hull taking the maximum beating from the surface swells. Once buoyant, the massive legs must be extracted from the seabed. Deep penetration creates a specific mechanical hazard. The legs rarely release evenly. 2 legs may pull free easily, while the third remains deeply wedged in hard clay. The floating hull acts as a massive lever against that single stuck leg. The towmaster must actively direct the tugs to thrust against the current and wind, preventing the hull from applying twisting forces that could snap the embedded steel. Clearing this first procedural gate ensures the rig reaches full buoyancy with its cooling systems online and its leg guides intact. The timeline advances to Phase 2, transit afloat. The primary threat shifts to the loss of watertight integrity. Most jackup losses follow a predictable cascade of failure. Boarding seas wash over the low freeboard, tearing off hatches or vents and sending seawater pouring into spaces engineered to remain dry. This blueprint schematic details the rig's internal watertight subdivision layout. If a hull breach occurs, the water follows specific flow paths through the ballast tanks and void spaces, altering the rig's center of gravity. If the pumps cannot keep pace with the incoming water, the crew executes a counterintuitive damage control protocol. They intentionally flood the compromised compartment completely to the ceiling. A partially filled compartment creates a free surface effect, thousands of tons of sloshing water that actively destabilizes the rig with every wave. A tank filled entirely to the top eliminates the sloshing, converting the threat into static, manageable ballast. Preventing that scenario requires keeping the ocean out of the hull entirely, which means strictly adhering to mathematical environmental limits. This chart plots the allowable pitching or rolling motion. It dictates the exact combination of wave period and rig movement the design can withstand. The dangerous zone at the top left represents short wave periods combined with high roll angles. Entering this quadrant means the momentum of the elevated legs will likely compromise the jackhouses. The towmaster must alter course or heave to before the weather pushes the rig into this state. Because rig crews typically lack formal marine training, the towmaster enforces rigid hourly deck patrols and a strict permit-to-work system to ensure no watertight door is left unbolted. Relying on the allowable motion graph and hourly mechanical patrols is what keeps a routine transit from becoming a foundering statistic. Phase 3 is arrival and positioning. The objective is to navigate a massive, unpowered barge onto a precise offshore coordinate while balancing active environmental forces. This is a maneuvering diagram. It calculates approach angles by overlaying a rig outline onto a directional compass rose. The towmaster plots the exact environmental vectors onto the template, mapping a 1.5-knot tidal stream from the northeast against a force 5 wind from the south. Using these vectors, they deploy the tugs to the port, starboard, and lead positions, assigning specific horsepower to precisely counteract the incoming wind and current. The rig stops 250 feet short in a standby position. High-tension anchors are run out from the bow and stern, holding thousands of pounds of tension to manually winch the barge into its final slot. The operation reaches its point of maximum stress during tagging. The legs are lowered back through the water column, preparing to strike the unseen seabed. At the exact millisecond the spud can touches the mud, the barge must be perfectly stationary. Any lateral drift across the ocean floor translates into massive bending stress, which can tear the internal leg guides from the hull. Positioning a rig requires the strict mathematical neutralization of dynamic ocean forces by pre-calculated tug horsepower. In the final phase, the rig elevates. The jacking pinions engage, pushing the hull up until it clears the waves with a 5-foot air gap. But drilling cannot commence until the rig clears one final mandatory test: preloading. The rig opens its sea valves and intentionally pumps thousands of tons of seawater into its internal preload tanks. This massive artificial weight proves the bearing capacity of the seabed, ensuring the legs won't unexpectedly punch through the crust during a future storm. Once the water is dumped and the rig jacks to its final height, the rolling barge is replaced by a rigid, stationary platform. Completing a move from pin to pin requires actively managing transitions between conflicting physical states. The Jackup is engineered strictly for stationary drilling. Moving it across the ocean relies entirely on the discipline of the marine crews, who use mathematical modeling and precise horsepower to compensate for a compromised design.